Today we discuss about the experimental methods of X-ray diffraction. To explain X-ray diffraction experiments, there are three main methods to determine internal and crystal structure of a solid material. These three methods are: the first one is Low diffraction method, second rotating crystal method, and third one the powder method. All these three methods, which based on the same principle of the Bragg's law. The Bragg's condition, it is 2d sine theta equal to n lambda, where d is the interplanar spacing, theta is the Bragg's angle, n is the order of diffraction, and lambda is the wavelength of X-ray used in that experiment. Now, when we discuss all these methods, now in each and every experiment, there are different variable terms. These variable terms we explain here by using this tabular form. If we considering this Low method, that method having the three variable terms: sample, wavelength of X-ray used, detector, as well as the diffraction angle. Hence, the sample used in Low's method should be single crystal. The wavelength of X-ray used in that case must be variable, means we use white X-rays or continuous X-ray beam. Detector, which is used for recording the reflected X-rays or diffracted X-rays in that experiment. So, photographic film is an important parameter in that experiment. The diffraction angle should be kept fixed. For rotating crystal method, again, this method uses single crystal. The wavelength of X-ray should be fixed, means monochromatic X-ray beam is we use in that experiment. The detector should be photographic film or the radiation counter, and the diffraction angle should be variable. Last method, that is powder or debaucher method. Here the sample is not in the form of single crystal or the polycrystal, but that crystal or the solid material which crushed in the powder form. So the sample must be in the powder form. The wavelength should be fixed, means again monochromatic X-ray beam is used in that experiment. The detectors should be photographic film or the radiation counter, and diffraction angle should be variable. The Low diffraction method is the best suited for the determination of the crystal orientation, and it also quickly verify the crystal symmetry in a given crystal. The schematic representation of the Low diffraction method is shown here. This method consists of the continuous X-ray beam source, single crystal, and the detector that used as a photographic film. Here the single crystal is held stationary in the path of the X-ray beam, and which is fixed on a goniometer head. The goniometer, which gives the best alignment of the crystal, which is exactly normal to the direction of the incident light. Here the separation between the crystal and the film is very small, that is 3 to 5 centimeter, so that the number of reflection intercepted on the film goes on increasing and it reduces the exposure time. Here the film B, which record the back reflections, and the film A, which also record here this reflection X-rays from that crystal, and it gives a resulting pattern. That pattern we call love pattern. When X-rays are scattered by certain group of the parallel atomic planes within the single crystal, the resulting pattern shows series of the spot in definite order. Here, the resulting pattern indicate the regular arrays of atom, and from that result we get what is the actual orientation of a given crystal. Means that each spot on that pattern gives the crystal orientation of a given material. Love diffraction method is also used to assess crystal perfection from its size and shape. Now we see the next method, the rotating crystal method, which is useful in determination of the crystal structure when single crystal is available. Its schematic representation is shown here. In that method, it mostly consists of the collimator, cylindrical camera. The specimen is in the form of the single crystal, and that single crystal is held on the goniometer head. Now, what is the function of each and every term in that experiment? The collimator. Here, in rotating crystal method, mostly we use the monochromatic X-ray beam. That monochromatic X-ray beam is passing through the collimator, means the light becomes fine and sharp, and it must be parallel. Parallel beam of light, after passing through the collimator, it passes through the cylindrical camera, through the inlet here, and when it incident on the single crystal, that single crystal is rotated about an axis. The X-rays, after reflection, the X-rays exit through this another point that we call the X-ray exit. Here, the direct beam stopper is also kept at the exit point of the X-ray beam. Now, actually, how the diffraction pattern we get in that method, when the monochromatic beam, means the source used is the monochromatic, that monochromatic beam of the X-ray, when allowed to fall on the single crystal, that single crystal is rotated about an axis. That axis of the crystal and or the rotation axis and the axis of the cylindrical camera, both are on the same line, means both are coincidence. When that X-ray falls on this single crystal through the collimator, then X-ray reflections are recorded on the X-ray film, which is fixed inside the cylindrical camera. Now, the X-ray beam, X-ray film, which is surrounded inside the cylindrical camera. The diameter of the cylindrical camera is 3 centimeter. Now, what is the typical reflection photograph when we expose the film and develop? It is shown here. The resulting photograph shows all diffracted rays which lies on the series of the concentric cones, that cones we just shown here, all the cones having different order of the diffraction surrounding the rows of the atoms. These cones are responsible for the formation of the layer lines in rotation photograph. Here these are the layer lines, zero layer line, first layer line, second layer line, similarly below one. That these layer lines are responsible, the formation of the layer lines which are coming from the diffracted cones. So all reflections on the zero layer line which comes from the planes which are parallel to the axis of rotation, corresponding to its Miller index is 0. The position of the various reflections on this layer line, depends on interplanar spacing d. Here, as we suppose higher spacing, the X-rays diffract at lower angle and it corresponds to reflections are nearer to the center of the film. Here that center of the film which corresponds to exit point of the direct X-ray beam, which corresponds to 0 Bragg's angle, and other layer lines which are separated by S1, S2, S3 and so on. Such a rotating crystal method is helpful for determination of crystal structure only when the crystal must be in single crystal form. Otherwise, it is impossible to find the crystal structure of a given material by using the rotating crystal method. Now we see the next method. Here the powder method or Diffraction method is more convenient method as compared to earlier two methods, since this method is readily applicable to all crystalline materials. The resulting diffraction data are unique and it can be used to identify a given material. Now, what is its experimental setup? That we shown here by using the schematic diagram. Powder method experiment, which consists of X-ray beam source, filter, collimator, sample holder, which is kept at the center of the cylindrical camera. That cylindrical camera is also known as Debye-Scherrer camera. And inside the cylindrical camera, a photographic film is fitted such that it records all the diffracted beams from a given powder sample. Now, what is its principle? Before explaining the principle, you must know that now what is the role of each and every part in that experiment. S is a continuous X-ray beam source. We make it monochromatic, and for the monochromatic source, as we need, we use the filter. Hence, the filter is a window of the material that absorb undesirable radiation and it allow to pass only the required wavelength beam. And therefore, the continuous X-ray, it becomes monochromatic by using the filter. If such a filtered monochromatic X-ray beam passing through the collimator, that collimator which consists of the number of slits, it becomes fine, narrow and parallel beam when it passing towards the powder sample. Here, inside at the center of the cylindrical camera, the sample holder is kept at the point P. That in that holder, the given material is crushed in the form of very small minute particles. Each particle will acts as a small grain, crystal grain or crystallite. In that grain, the certain set of parallel planes which will gives the resulting diffraction when that plane is correctly oriented in the direction of incident beam. Such a different orientation of the planes will form different diffraction cones, and that from different diffraction cones we get a resulting diffraction pattern which is recorded on the photographic film. Here we are considering a one of the plane which is formed by the most of the crystallites. That plane is M dash. That plane which makes angle theta with the direction of the incident beam, same angle with the direction of diffracted beam. Therefore, the total angle becomes 2 theta. Such a particular set of plane, when X-rays gets diffracted from that plane, it forms a one particular cone with the angle 2 theta. Such a diffract, that is the coaxial cones. Coaxial cone means the axis of that cone is exactly along the direction of the incident beam. Such a coaxial cone of the diffracted rays will strike on the photographic film at the position A. Suppose that point A is at a distance r from the center point O. At the point O, when directly X-ray beams strike on the film, that point is O. On either side, we get the different diffracted X-ray beams strike on that film at the different points, and the resulting film shows the different arcs on that film. Now see here, before that we explain what is the principle of that experiment. If the monochromatic light is allowed to incident on the powder sample, in that sample, the most of the crystallites which are randomly oriented, in that the certain number of the crystallites or the small grains which will form a particular set of plane, and that plane, when it forms the correct angle with the direction of the incident beam, then only reflection is possible and it satisfies the Bragg's law. While another fraction of grains will form another set of planes, that plane also correctly oriented in the direction of the incident light, and therefore reflection is also possible from another set of the plane. In that way, the number of reflections are possible from the different sets of the plane with different orders for such a set. If all orientations means same interplanar spacing, all that reflected rays from the same orientation will form the one cone whose semi-vertical angle is 2 theta. Each set of the plane, for each order, there will be a one cone. Their intersection with the photographic plate with the plane normal to the incident beam will form the series of the concentric circular arcs, the radii of each arc with the glancing angle theta we get from the resulting data. Hence, as the glancing angle theta is known, wavelength lambda that is fixed, then the spacing between the plane we can easily determine using powder method. Hence, what is the resulting pattern? If the film is developed, that film is taken out. This film shows just like the center point O when X-ray directly strike at this point, theta is 0. As theta goes on increasing, very near to the center point, we get very small cone is appeared for one particular set of plane. It forms the circular arcs. As theta goes on increasing, the arcs also away from the center and it goes on increasing. Theta approaches to 90 degree. These cones which we strike on the photographic film becomes flat. Again, theta increases beyond 90 degree. Then arc which appear on the film, that is traces which gets reversed, and exactly at 180 degree it becomes circular. How we analyze a given sample and its crystal structure, that we explain in the next lecture. Before that, how we determine the interplanar spacing of a given material by using powder method, that we explain here. Here we consider one particular set MM dash whose semi-vertical angle is 2 theta. When from that plane X-rays gets diffracted, the diffracted X-rays strike at the point A. The point A is at a distance r from the center point O, and therefore we find what is the arc of this cone which is appeared on that photographic film, that we calculating here. We consider L is the radius of the camera from center point to O. That radius is we taken capital L. Then what is the glancing angle 2 theta? The 2 theta equal to arc divided by radius. Means we get one relation, theta equal to r divided by 2l. Means 2 theta equal to r divided by l, or theta equal to r divided by 2l. That theta is in terms of the radian. Then we measure in terms of degree. Therefore, we multiply by this term 180 degree divided by pi. Therefore, the glancing angle theta we measure in terms of degree. The relation becomes r divided by 2l into 180 divided by pi. Hence, we can easily determine the glancing angle theta for each and every set of parallel planes. Those are randomly oriented in a given sample. If theta is known, then it becomes possible to find what is the interplanar spacing between the parallel planes. Now, how we find the interplanar spacing D? Since the Bragg's condition, each and every set satisfy the Bragg's condition, 2D sine theta equal to lambda. If lambda is fixed in that experiment, X-ray, monochromatic X-ray beam is used, lambda is fixed. Theta we getting from the resulting diffraction pattern. That theta we measure whether in terms of the radian or the degree. Hence, theta and lambda is known. Then it becomes possible to find interplanar spacing. And if that interplanar spacing for a given material is known, then it becomes easy to understand. Now, what is the nature of the crystal structure of a given material? In the next lecture, we discuss in detail about how powder method is used for analysis of cubic crystal structure. Thank you.